let me just take a few minutes just to kind of give you the big picture of where we're going. So, chapter 6, the goal of chapter 6 basically is to motivate and in some sense derive the Jordan's canonical form. So, let me just kind of sketch for you the basic steps in this argument. Section 1, we discussed triangularizability. Basically, the result which is proved in section 1 of chapter 6, the mono little, is that if you have a linear transformation on a finite dimensional vector space over a field F, and it is such that the characteristic polynomial has as many roots as the dimension of the space. All right, so in that case, you can find a basis, and with respect to that basis, you can make the matrix for that linear transformation be upper triangular. This corresponds to the existence of what you could call a fan basis. Although they don't call that. I was reading Serge Lang's linear algebra. He calls it a fan basis. But anyway, I'll try to prove this probably Monday. Nilpotent maps is section 6.2. A nilpotent map is one for which there's some finite power with which you can compose the map and you get back to 0. And yet the k-1th power of that map is not equal to 0. So this not being equal to 0 means that there is something in the kernel of this map which is non-trivial. And turns out you can build those from eigenvectors. You can find like eigenvectors for n, and then there's a systematic way of building the basis for these nilpotent maps as described in section 6.2. I'm not going to try to do it all right now. There's a systematic way you can build these. It's very much like that t-cyclic basis problem I gave you in the last homework. It's very much like that. You take one vector and you keep operating by n and you build this basis. The difference is that once you get to this, you end up being able to prove that there's some basis of vectors, and then when you go past that sort of t-cyclic, in this case n-cyclic basis, you go back to 0. So that the matrix that you get, it looks like that basis, that matrix you got for the t-cyclic basis, except instead of having that last column with non-zero things, you get something like this. So zero's on the diagonal. 1's on the super diagonal. Maybe I might be slightly off. I'm trying to remember. I'm not sure about that 1 there. I think it's there though. Anyway, don't worry. We'll spend a day on it. Get into the details. That'll probably be Wednesday. And then sections 3 and sections 4 of chapter 6 define the Jordan form. And so basically, the argument goes something like this: you look at things. You look at something. Basically, this is not quite accurate, but essentially this: you look at t minus lambda I, and t minus lambda I, at least the restriction of t minus lambda I to a particular subspace is nilpotent. Right? And since it's nilpotent, that means you can apply the result of section 6.2. You can choose a basis so that you can basically choose, this is n with respect to a particular choice of basis. So with respect to a particular choice of basis, you can make t minus lambda I with respect to that particular choice of, oh, I'm sorry, I can't make up my mind. My mate is like anti-gravity or something, it's flying out. I mean, that's the right. Oh, anyway. Okay, so then this is going to be like, let's just take the case of 2 by 2, okay? So 3 by 3, how about that? 0, 0, and then 1 and 1. If it was, say, 3-dimensional, it would look like that. But then, what does that mean? That means that the matrix of T with respect to beta will will look like what? It will look like lambda, 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 1, 1, 0, 0, 0, 0, for example. So in this way, we combine 6.1 keeps getting used. There's theorems by invariant subspaces, which we use throughout the rest of the chapter. Anyway, so this thing I just wrote for you, this is a Jordan block, or the Jordan form. Jordan form. Jordan form, let's just say. It's a Jordan block with a eigenvalue lambda and a multiplicity. Well, the geometric multiplicity corresponding to such a thing would be 1. The algebraic multiplicity would be 3. You see, if T permits a basis that makes its matrix look like that, that means it's not diagonalizable. Okay, there's only one eigenvector. I can tell that, given this discussion. And if it turns out that the matrix for T can be similarity transformed to that, that means that you don't have enough eigenvectors to diagonalize. So anyway, ultimately, that's what we want to explain is how you can find the Jordan form. But here's the thing. The ultimate theorem that we prove is this, at least for T from V to V over the complexes, there exists a basis beta called a Jordan basis. And with respect to that basis, what you have is that T beta beta is equal to like a bunch of Jordan blocks. So first one might be lambda 1, lambda 1, da da da, lambda 1, and 1s. Zeros up here. And then you might have lambda 1, 1, like that next. And you might have some lambda 1s like this, even. But that's it. You have Jordan blocks for lambda 1. You can have 3 by 3 blocks. You can have 2 by 2 blocks. But it's always these blocks or singletons or single elements with 1s on the superdiagonal. And every time you have one that doesn't have, every time you have one in here which doesn't have a doesn't have the superdiagonal one, that corresponds to the existence of an eigenvector with eigenvalue lambda 1. That's what's going on here. So like, with what I've written so far, I get this corresponds to eigenvector, there's an eigenvector here, there's an eigenvector here, there's an eigenvector here. All right? So with what the example I've written, there would be 4 eigenvectors. Now, and then you keep doing the same for the rest of the eigenvalues, lambda 2 throughout lambda k, however many eigenvalues you have. For each one of those, you get these blocks on the diagonal. And so up to reordering of the blocks, this is a unique representation of T. It completely describes the structure of T for a complex linear transformation. It tells me everything about the eigenvectors and about what's past eigenvectors to describe. So let me show you. Let's look at it. Let me look at a specific example because it's hard to see what I'm saying when we look at a general example like that. So let's look at something more specific. Suppose I have, let's say 2, 1, and then let's say 2 and 3. So 4 by 4, okay? So to keep it simple, I've already put the matrix into Jordan form. I want to understand what it means when a matrix is in Jordan form. What does that say about the standard basis with respect to the matrix? All right. We know from our discussion of diagonalizability that diagonal form is especially nice because that means that everything in the standard basis is an eigenvector with eigenvalue corresponding to that diagonal element, right? Yeah.
Is Jordan form just like upper triangular, or is it?
It is a, right, it is.
Super.
Good, good. So you know upper triangular is possible from section 6.1, but this is even more special. The upper triangularization is not unique. However, the Jordan form, up to reordering of the blocks, is a unique representative of all linear transformations T which are similar to T. So any similar, any other T which you could, you know, any other matrix, let's say T beta beta, which you could reach from doing a similarity transformation, they would have the same Jordan form up to possibly a reordering of the blocks. So do you remember before in this course, when we had a linear transformation from V to W, we proved that there was a basis which made the matrix of T have the identity padded with zeros, where the identity was the size of the rank of the matrix. That was a unique representation of that linear transformation. In some sense, that categorizes what's going on as much as you can. But there we were allowed to adjust the basis and the domain and the basis and the range separately, right? And that's what allowed us to massage the thing until we had the matrix, the identity matrix. And here, on the other hand, we're considering the same vector space in the domain and the range, right? And we're putting the same basis before and after. So it's much more restrictive in the way you can change the matrix into another matrix, right? And because of that, this turns out to be the representative for all such matrices. Any matrix which is similar, excuse me, any matrix, if this is A, right? If you chose another matrix B, and B was similar to A, it would actually have the same Jordan form. Anyway. Fun. Okay, so check this out. A. All right, so A minus 2i, what's that look like? Yeah. Oh, 3 minus 1 is 1. Yeah, 1. Sorry. It's a 0, sorry. So you can easily see from this what? I mean, you can see it a lot of different ways, but certainly A minus 2i times E1 is equal to what? False. So A minus I, the first column is what? 0, 0, right? What's it? That makes E1 what?
The eigenvector?
Yeah, E1 is an eigenvector for A with eigenvalue 2. And the same story for 3, right? This is 0. So, on the other hand, E2, it's funny, right? What does it give you? That's actually what? E1, yeah. So that says that E2 is not an eigenvector, right? With eigenvalue 2. Right? I guess we can also, while I'm at it,
oh, is it because you need it to equal 0? Did you set it equal to 0? So that's why that was not?
I didn't set it equal to 0. I calculated this matrix times that, this matrix times that, this matrix times that, and I got 0. So I'm not solving an equation, I'm making an observation. You know, by the way, you can calculate the A minus 3i times what? Times E4 is equal to 0, right? I don't want to write that matrix out, but you can see that, right? So we have how many eigenvectors for this matrix? We've got 3 linearly independent eigenvectors, so this matrix is not diagonalizable. Because we proved before that a diagonalizable matrix is diagonalizable, but only if it has an eigenbasis. This does not have an eigenbasis. I guess I haven't proved it doesn't have an eigenbasis, but that's part of what we'll prove in chapter 6. So let's see here. What is the deal with E2 is really the question, right? Check this out. If I take a minus 2I squared on E2, that's what? That's a minus 2I times a minus 2I times E2, right? What's this?
E1.
Yeah.
0.
Yeah, 0. And so this means that E2 is a generalized eigenvector. Generalized eigenvector with eigenvalue what? Well, in this case, lambda equal to 2, right? So I mentioned something over here called the Jordan basis, right? This Jordan basis I'm talking about, the Jordan basis is formed from taking all the eigenvectors you can find for the matrix and then adjoining to that generalized eigenvectors. Turns out, if you throw in generalized eigenvectors, you can always get a set of n linearly independent vectors. And you can arrange the generalized eigenvectors in such a way that with respect to that eigenbasis, you get this Jordan block decomposition. So here the standard basis is a Jordan basis because it's already Jordan blocks. Now, what would the characteristic polynomial for this be? It's a triangular matrix, right? The eigenvalues are on the diagonal, so you can just write it out. It's
minus 2 cubed.
Yeah, 2 minus lambda cubed times 3 minus lambda. There you go. There's the characteristic polynomial. So one of the nice things about Jordan form is if you have it, you can read off the eigenvalues. Okay. So anyway, that's where we're going. We want to understand this Jordan form as carefully as we can. Let me give you a definition for generalized eigenvector. So definition, if A is a n by n matrix, then the x not equals to 0 is generalized eigenvector with eigenvalue lambda and order p when a minus lambda I to the, let's say here, p minus 1, x is not equal to 0, yet a minus lambda I to the p x is equal to 0. You could also define the generalized, you could also define like the generalized eigenspace, right? Generalized eigenspace would be, generalized eigenspace of order p would be something like what? Well, that's not quite I mean, I don't know. I'm not 100% sure about this this condition here. I mean, I like it for the sake of making things interesting, but anyway, let me not talk about what I'm not sure about. So one way you can get this, right, is by building what's called a chain, right? So idea of a chain. So here's a chain. If I have, suppose I have suppose I have A minus lambda I. How do I do this? So suppose I have A minus lambda I, let's say xk is equal to xk minus 1, right? And then suppose I define A minus lambda I xk minus 1 equal to xk minus 2. See where I'm going with this? And down the line, I get to A minus lambda I x2 equal to x1. And finally, A minus lambda I x1 equal to 0. If I have this structure, that makes x1 a what?
It's an eigenvector.
Right.
Just normal eigenvector.
And let's see, so this, I'm going to do a couple things. One thing is to look at this. This says that ax2 is equal to what? It's equal to lambda x2, right? Plus x1. And then so on up the chain, this says that axk minus 1. Well, let me do the last one. It says axk is equal to lambda xk plus xk minus 1. Right? This one says what? It says ax1 is equal to what? Lambda x1. So one of the things you can, if you had this chain structure, right? If you were to say, let, and then suppose that these were linearly independent, all right? And if you were to say, suppose A is k by k also, then you had x1 through xk as a basis for Rn. Then if you think about it, you know, if you look at L of V equals to AV, the linear transformation induced by A, what's the matrix of L with respect to the beta basis? So, you know, I would start with L of x1 beta coordinates, right? Well, I don't have enough room to write the intermediate step. We're going to have to think about that in our brain. Well, where else would we think? On the computer. No. So this tells me that ax1, which is, right, the linear transformation L, you know, L of x1 is equal to lambda x1, right? But if x1 is the first thing in the basis, that just gives me lambda e1, which is written this way, right? Well, let me use lambda e1, sorry. I'll make up my mind eventually here. Lambda e1. The next thing, I get lambda e2 plus e1, right? And so forth and so on. Eventually I get to lambda ek plus ek minus 1. And if you write that out with ones and zeros and all that good stuff, what do you got? You got lambdas down the diagonal. And you have a super diagonal of ones. See, in the second column, you have a 1 here. That's E1. And all the way down to the kth one, you've got a 1 up the lambda. So there. Now I am sure that I was supposed to write. I'm now sure I was supposed to write this 1 here. I have no reservation about it now. Not that I've proven anything, I'm just telling you. So these ones continue. And that's a Jordan block. It's a k by k Jordan block. It corresponds to a k chain. All right? This k chain, basically what you do, you start with x1, right? What's the next thing in the chain? It's a minus lambda I times x1, right? What's the next thing? So this is base of beta. Actually, if you look at it, it's being generated from this, right? If I call this thing t, just to give it a name, you got t of x1, you've got t squared of x1, you've got t cubed of x1, all the way on out until you get t to the.
Isn't a minus lambda I times x1 just 0?
Oh,
Would you start with xk?
bummer. Oh yeah, sorry. Yeah, that's the thing. That's the pesky thing, is you don't start with the eigenvector. You actually have to start with the thing, not the eigenvector. You have to start with the thing that's the largest generalized eigenvector in this chain. Sorting out how to do that, in general, is a lot of what 6.2 is about. These tableaus give you a method for sorting through that and proving the linear independence of lots of these put together. It's subtle. It's not entirely trivial. And you're right, I do get K there. And here and everywhere. But the point is, once you got one, you just, how many? I guess that's the other thing I was going to show you. The second calculation I was going to show you is that this tells me what? This tells me that a minus lambda I squared x2 is equal to 0, right? And so forth and so on. The top one will get a minus lambda I to the k power times xk is equal to 0, right? So that's an order k generalized eigenvector at order k there.
Why?
Why indeed? This one we just calculated over here. Because when I apply the t once, it brings me down to 1. If I apply it again, so like at k's order, the first application brings me down to k minus 1. The second one brings me down to k minus 2. The third one to k minus 3, and so forth. Dum, 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 dum. Eventually, you're left with a minus lambda I times x1, which then is 0. If you don't like that, you can make an easy induction argument based on this. So anyway, that you can generate an eigenbasis, generalized eigenbasis from the highest thing in the block. The question is, how do you find the highest thing in the block for a given matrix, right? I'm not sure I'll really do justice to answering that question. I'm going to explain to you what you have to look for, and I'm going to explain to you theoretically what does Jordan blocks do for you. So with that, I want to go back and talk about applications and geometry a little bit more. I've given you a picture ahead where we're going. You notice all of this is for complex matrices, right? The book doesn't even talk about the real case. The book only talks about the complex case. My notes discuss the so-called real Jordan form, right? Because you notice that these characteristics, this criteria of all of the roots being in F is not satisfied for a rotation, for example, in the plane, right? Remember? If I have A equals to, cosine theta minus sine theta, cosine theta, that gives me P of lambda is equal to what? I mean, it's lambda minus cosine theta quantity squared plus sine squared theta. So therefore, lambda equals to cosine theta plus or minus I sine theta. Those are your zeros. So yeah, in the complex, if we view this as a complex matrix, we're good to go, right? Hey, Lou?
Yeah, on that part.
Okay.
Right.
So for the complex case, we're good to go, right?
Yeah.
But if we're only allowed to work in the reals, this isn't going to do it. But we already know what we can do for this, right? We know that we can choose the basis of real and imaginary parts for the complex eigenvector. And so we can, in fact, this is already in its real Jordan form. This is the real Jordan form of a matrix. So, if I had something more, you guys saw the things, right? Like if I had, what, like 1, minus 1, 1, 1. You can put that into real Jordan. I mean, that actually is also in real Jordan form, sorry. Yeah. So the bottom line is, what I describe in my notes, and I probably shouldn't get into right now, but it seems like I'm on that path, so here we go. If you had something like a complex Jordan form, you know, you can have complex Jordan, you can have complex eigenvectors. So you have something like I, 1, minus I, 1. That could happen. This would be if you have one complex eigenvector. If you had one complex eigenvector and one generalized complex eigenvector, that's what your Jordan block would look like. Now, the corresponding real Jordan form would look like what? Let's see here. Oh, should I keep something I? If this is I, this is what? Cosine theta is what? Pi over 2, right? So sine theta is 1. Sorry, if I in the complexes, if I do a similarity transformation and I end up with I minus I, right? Then that relates to the real Jordan form corresponding to that is what? It's, I think it's 0 minus 1, 1, 0. So let's see, how's it go? I believe the real Jordan form will be 0, minus 1, 1, 0, 0, minus 1, 1, 0, and then you end up with blocks up here. So something like that is the real Jordan form. But this is explained in detail in my eigenvector chapter. But that's not in the book. Yeah.
So you get like the same even though the i's are negative in the bottom one? You get the same as you do for Boston?
Right, just like here, remember to get to this, I really can just focus on that. I look at you know, AU equals to IU essentially. I get U equals to A plus IB, right? And then I do the similarity. I do A, B, inverse A, AB, and out pops. Well, I may have the minuses askew. I'm not 100% on my minuses. I maybe the other way around, but something like that is the real Jordan form. This is hard to find in books, but it's in my notes. Because books like to focus on the complex case, which is beautiful and nice and tidy, and doesn't have this extra little wrinkle. But this extra wrinkle matters for applications, right? If you're solving differential equations, for example, you kind of need to know about this because some of your differential equations correspond to having a system of coefficients, for example, that have complex eigenvalues, and you need to know how to solve it even when you have that, right? So I want to talk about some applications of all this. I want to show you a little bit about why Jordan form is just so amazing for applications. I think I'm gonna focus on the problem of differential equations here for a bit. So I would point out, by the way, okay, so here's the problem. What's our problem? We want to solve things like x prime equals to x plus y, and y prime is equal to, I don't know, x minus y, something like that, let's say. You can view that instead as x, y prime equals to 1, 1, 1 minus 1, x, y, right? And so if you look at it, let's just look at it in a slightly better notation. We're really trying to solve what? We're trying to solve dB dt is equal to AB, where A is some constant matrix, right? I mean, you could try to do this. Can you guys tell me some eigenvectors for this matrix A? Or have I made my matrix too? Okay, tell you what, guys, let me be more boring. Let's make that minus a plus. Then I can definitely just read off the eigenvalues for you. If I make this a plus, what does that say? What is definitely an eigenvalue? Remember, a matrix is invertible if and only if what? Lambda equal to 0 is not an eigenvalue. But also, a matrix is invertible when it has linearly independent rows and columns, right?
So with 1, 0 or something?
I'm saying 0 has to be an eigenvalue is what I'm trying to say, right? Because this clearly has linearly independent rows and columns, right? So what is the eigenvalue? What is the eigenvector with eigenvalue 0? I'd say it's pretty obviously 1 minus 1. Right? So there you go, there's an eigenvalue. Eigenvector with eigenvalue 0. And let's see here, what's the other eigenvalue?
1, 0, I don't know.
You don't know?
I don't know.
How about this? What if I do a times 1, 1? 1 plus 1, 2. 1 plus 1, 2. So the other eigenvalue is 2. Of course you could calculate the characteristic polynomial, but that seems like it would be too easy. So I'm just using guessing instead. So my point to you is we have eigenvector 1 minus 1 equal to v1, and eigenvector 1, 1, let's say equal to v2. Lambda equals to 0. Lambda equals to 2. The solution to this differential equation is as follows. X of t is equal to c1 e to the 0t times v1 plus c2 e to the 2t 1, 1. That's how you solve it. Simple as that. You're like, well, e to the 0t is just 1. Why don't you just write 1 here? Fine, I'll do that. You're like, well, how do you know that that's a solution of the differential equation? Well, because it's easier to prove it in general than it is to prove it for that example. Right? So here's proof. Suppose you have x of t is equal to e to the lambda t times v, where a v is equal to lambda v for v not equal to 0, right? In other words, suppose I have an eigenvalue lambda for my matrix A, and suppose I have an eigenvector v. I'm arguing that if you take e to the lambda t times the eigenvector, that gives you a solution to the differential equation. dv dt equals to a. So here's how it goes. So you take ddt of e to the lambda t times v. What happens? That's a constant, so it pulls out. Right, it's constant vectors. You pull it out of the differentiation. What's the derivative of e to lambda v? Right, so that's lambda e to the lambda t times v, but you can group lambda and v, and what do you get? Lambda v is what? It's ab, right? Because v is an eigenvector. And then you put the lambda back where it belongs, because it's a scalar. And that, by definition, is v. Excuse me, that is x, rather. So this is a times your x. And I started by differentiating x, right? So what I've just shown is that x so constructed solves the differential equation. So you see, to each eigenvector that we can find for a constant n by n matrix over the reals, we get a solution to the corresponding differential equation, dv dt equals to ab. But you know that's not enough to solve the problem in general, because you could have what? You could have complex eigenvalues. Or, worse yet, you could have not enough eigenvalues altogether. I mean, you could have not enough eigenvectors also. You could have a combination of those two things. You could have complex eigenvalues and not enough complex eigenvectors. All of these things can happen. And all of those different cases are, I have them in the last chapter I provided for you guys, which I don't cover in its entirety because this is in differential equations. I show you exactly how to solve all those different cases in view of the Jordan form. I'm going to focus on the real case here. So we're going to assume that let's assume A has n real eigenvalues. Oh, can you tell me a case for A where the thing I just showed you would suffice to build like n of the solutions? What if A was symmetric, right? We already know that there's no orthonormal eigenbases. So in the symmetric case, what I just showed you would be enough to solve the differential equation. By the way, there's a theorem that says for an nth order, for n equation, n differential equations in n variables, the general solution has to be built from these two linearly independent solutions. And this is a way of generating them. But let's get back to the interesting case. Suppose A has n real eigenvalues, but not enough eigenvectors. All right? Well, you don't have enough eigenvectors. What gives this Jordan form for you? Right, so and let's make it relatively simple. Let's think of A basically being the kind I just erased here. So it's a k by k. Let's suppose that basically, suppose A is k by k and as eigenvalue lambda with algebraic multiplicity k. In other words, the determinant of A minus lambda I is simply equal to, I need a different notation for the, let me use an x here for a second. A minus xi is just equal to like lambda minus x to the k power. In other words, you just have the repeated root of lambda k-fold times, all right? And I'm also going to rain on our parade and say, but the dimension of E lambda is equal to 1. So in other words, I have just one eigenvector, right? So it's kind of sad. Sadly, we just get x of t equals to e to the lambda t, let's say times x times v1, where a v1 equals to lambda v1. That's all I get for an eigensolution. But the thing is, this differential equation, if you think about, dv dt equals av needs k solutions. So the obvious question is, where are the other k minus 1 of them? The answer is the Jordan form. So I'm going to show you something I call the magic formula, because it's magical. And so here it is. And I'm also going to introduce you to something that you may not have seen before. I mean, you probably haven't seen it before. It's the so-called matrix exponential. The matrix exponential is this. So you take e to a matrix, let's say B. And the way this is defined is you take I plus B plus 1/2 B squared plus 1 over 3 factorial B cubed plus, you get the idea. So you define the matrix exponential by its power series. But you notice this is a sum of matrices. It's really something new. But there's some nice properties, right? So if AB is equal to BA, then you can show that e to the A times e to the B is equal to e to the B times e to the A. Although it's not generally true that you can commute them. And you also get that this is equal to e to the A plus B. That's a special case. Generically speaking, there's something called the Baker-Campbell-Hausdorff relation. You need more complicated. E to the 0 is what? Right. by 1 you mean the identity matrix, right? And the matrix exponential is always invertible because e to the a times e to the minus a is equal to e to the a minus a, because surely a commutes with its negative. So as you can see, the matrix exponential is invertible, right? That shows you that whatever a you now, provided this converges, which there's a question there, why does that converge for an arbitrary matrix, right? It's not obvious, but it does. Proof is my notes. Then you can calculate this matrix exponential, and if it converges, it's got an inverse. Which means that the matrix exponential always has resting inside of it, for a k by k matrix, k linearly independent columns. You're like, okay, well that's lovely, but who cares? Well, I mean, I care. So the magic formula is this.
Is that, Dr. Greg, is that exclamation point after solutions, is that for excitement? Or
That's factorial
is that factorial?
and excitement. Yes.
So it's factorial?
Yes. So e to the ta, all right, is equal to what? Or maybe I should say lambda. Yeah, lambda. E to the lambda a. No, e to the ta. Excuse me. I'll get it eventually here. E to the ta is equal to e to the well, gee, I don't know. Tilt your head, squint. You can see that this is really t times a minus lambda I plus lambda I, right? I just added 0. And so what that really is like, gee, I don't know. It looks like a e to the t times a minus lambda I, well, plus lambda I t. But you can prove that that is the same as e to the lambda I t, e to the t times a minus lambda I. Fun fact, matrix exponential of a diagonal matrix is the diagonal matrix of the exponentials of said diagonal matrix. But in more interesting and simpler terms, this just converts to the ordinary exponential, like so, times I. That's an identity which is known. And then this guy, aha, think of that t times a minus lambda I as being the quote-unquote b. Think of this as being b. Right, so what do you got? You got I plus b plus 1. So this gives you the identity matrix plus t times a minus lambda I plus 1/2 t squared times a minus lambda I squared. And the factorial, yes, sure, factorial. T cubed, a minus lambda I cubed plus da 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 da. And the reason I call this the magic formula is that when you hit it with a chain, when you hit it with an eigenvector or a chain of generalized eigenvectors, magical things happen. So, for example, this formula. What happens if we calculate e to the ta times, for example, v1, where v1 was an eigenvector with eigenvalue lambda? So, suppose a minus lambda I times v1 is equal to 0. What happens? See this? 0, 0, 0, 0, 0, and 0, and 0, and 0. It truncates this thing. Everything is killed by v1, except that term. And it leaves you with e to the lambda t v1. Of course, that is nothing more than the elementary solution I presented to you by just plain old differentiation of kind of an obvious guess. Right? That's the eigensolution. So when you hit the matrix exponential with an eigenvector, out pops eigensolution. But it's so much more than that. Suppose, I'm almost done, guys. Suppose a minus lambda I times v2 is equal to v1. We know from our earlier discussion that makes v2 a generalized eigenvector of order 2. What does that do to the magic formula? Hit that on the magic formula, what happens? construction, this is 0, which means any other higher power of it will also be 0 when it hits V2. What happens with this? When you have a minus lambda I times V2, you get this goes to V1. This stays V2, so what you end up with is e to the lambda t times V2 plus t V1. See guys, this is where the t comes from in the repeated root case in differential equations. If you're in differential equations, you know what I'm talking about. If not, it's okay. What happens when you have a generalized eigenvector of order 3? I'll just write down the answer. E to the AT times V3. The third thing in the chain, right? That gives you e to the lambda t, V3, plus t times V2, plus 1/2 t squared, V1, and so forth and so on. And so this gives us a general solution to the differential equation dv dt equals at. In fact, I could state the solution simply, elegantly, as follows. If I want to solve dv dt equals to AV, the solution is simply this. V is equal to the matrix exponential penta constant vector. That's the solution. End of story. Because that, folks, is nothing more than a linear combination of the columns of the matrix exponential, which I know contain all the solutions because I know I can hit with this generalized eigenbasis, which exists for any A and provides me these eigensolutions I'm showing you. But anyway, there's more to say to completely fill out the logic. What I'm trying to show you is once you understand the Jordan form and these chains, you can solve arbitrary problems that present themselves with matrices with constant coefficients. That's why I include this in the course. It's not just for me. It gives you power to solve a whole class of problems that you wouldn't even be able to touch without this technique. Am I over time? Yes. Sorry. Thanks, Sharon.
I didn't do anything today.
Anyway, I will try to be less flighty and just start proving my way through that next week.